Welcome to This Explainer. Today, we're diving straight into a massive, real-world collision, the explosive growth of artificial intelligence smashing right into our physical power grid. We're going to unpack a really rigorous forecast by researcher, inventor, and author Kevin L. Brown, just to see exactly what the data is telling us about this whole situation. So, before we even touch the power grid itself, let's talk about the tool we're using today. It's called Triune Harmonic Dynamics, or THD for short. Kevin L. Brown uses this THD framework to look at complex systems that are under stress. You can kind of think of it like a pressure gauge on a giant steam pipe. Instead of just, guessing what might happen, THD uses a very structured framework to measure the accumulating pressure inside a system. And by measuring that pressure, it actually helps us forecast exactly when that strained system is going to be forced to adapt or when it might just blow a valve completely. Here's our quick roadmap for today. We'll start by understanding the grid problem, then look at the THD pressure index, pinpoint the exact forecast timelines, explore the real-world grid implications, and finally, lock down the strict falsification parameters to keep all of this highly scientific. All right, part 1. Understanding the grid problem. There's this massive disconnect happening right now, isn't there? I mean, we all kind of think of AI as this weightless, infinite magic living up in the cloud. It feels totally invisible. But down here on the ground, the reality is heavy. AI requires massive, incredibly physical electricity infrastructure. All that rapid digital growth is quickly becoming a very real physical load, requiring data centers that literally suck up staggering amounts of electricity.
And here's the thing, you can't just plug a giant data center into the power grid like it's a new toaster. We're hitting severe grid choke points. Data centers love to cluster together near fiber optic cables and existing power hubs, which creates these huge local bottlenecks. Plus, this massive new electricity demand is arriving way faster than utility companies can actually build the new power lines. Add in long manufacturing delays for big transformers and intense local fights over the millions of gallons of water needed just to keep these giant computers cool, while the physical grid simply cannot move as fast as the software.
Moving right along to part 2, the THD pressure index. So, looking at Kevin L. Brown's THD research, the structural pressure index on our power grid is currently sitting at a massive 65 out of 80. Yeah, that is a super high score. It basically tells us that we're moving out of the early, easy stages of AI growth and entering a critical zone where the grid is seriously feeling the weight. Let's break down exactly why that score is so high. THD actually classifies this as late pressure. First off, pressure intensity is a 9 out of 10, simply because AI compute growth is driving electricity demand through the roof. Load concentration, also a 9 out of 10, because these massive data centers are crowding into specific towns and completely overwhelming local areas. And then there's the verification gap, sitting at an 8 out of 10. That just means utilities are really struggling to figure out which proposed AI projects are actually going to be built, and more importantly, who should foot the bill for the expensive power upgrades. Which brings us to Section 3, Forecast, Timeline, and Windows. With pressure this high, it's not really a matter of if the system reacts, but when. The THD forecast pinpoints an exact window for this, called a natural structural landing period. This period begins in July 2026 and runs straight through December 2027. During this specific 18-month window, all that invisible pressure we just talked about is expected to force a visible, real-world event. The system has to release the steam eventually, and the math says this is exactly when it's going to happen. Now, zooming in on that 18-month window, the highest risks land in what THD calls receiver pulse zones. Basically, these naturally align with times when the grid is already sweating. For example, late July to August 2026 is when intense summer heat waves cause peak grid stress because everyone's running their AC. Then, October to December is when utilities usually do their winter planning and file for rate changes. The pressure from these AI data centers naturally finds the weak points in the calendar, forcing hard decisions to be made. Okay, part 4, real-world grid implications. Just to be super clear here, Kevin L. Brown isn't predicting some apocalyptic grid collapse. We're looking at a few realistic scenarios instead. In a base scenario, you can expect to see local AI project delays, utilities scrambling to revise their plans, or local towns actively restricting data centers. Now, in an acceleration scenario, things get quite a bit hotter. We might see emergency utility warnings or a really loud public backlash over spiking power bills. Or there's the containment scenario, where tech companies might just decide to build their own dedicated power plants to solve the whole problem themselves. Actually, we're already seeing the pressure leak out. Early signs of adaptation are literally happening right now. Utility demand forecasts, which honestly used to be pretty flat, are actively being rewritten and pushed way, way up. Regulators are starting to push back hard to prevent regular homeowners from paying higher utility bills just to fund AI expansion. Tech giants, they're aggressively trying to lock down private deals for nuclear and gas power plants so they can escape grid limits entirely. And local communities are literally holding town halls to discuss zoning bans to stop the rapid building. And finally, Section 5, Falsification and Validation Parameters. To keep this totally objective and scientific, Kevin L. Brown set some very strict rules for how this forecast could actually be proven wrong or falsified. First, we have to look for visible grid conflict linked directly to AI. Second, we verify if AI demand naturally just slowed down on its own before breaking the grid. Third, and this is the most important one, if December 31st, 2027 passes without any major disruptions, rate fights, or AI project delays, then this forecast is officially weakened or falsified. If the system easily handles the load, the hypothesis fails. It's as simple as that. Because of this strict grading matrix, there is absolutely zero room for hindsight bias here. It's cut and dry. Either an event hits within the defined dates and matches the criteria, making it confirmed or strongly confirmed, or no event happens by the end of 2027 and the forecast is totally falsified. It's a highly accountable, completely transparent way to predict the future of our power systems. So what's the big takeaway from all this? It's that the digital boom is absolutely bound by physical limits. No matter how incredibly smart or advanced AI software becomes up in the cloud, it's eventually going to hit the hard, heavy, and very physical ceiling of our electricity infrastructure right here on the ground. You just cannot separate the software from the power it requires to run. And that leaves us with one seriously critical question to chew on for the near future. When this massive AI data center boom really hits your town, who's going to end up paying for all the necessary power grid upgrades? Will the multi-billion-dollar tech companies foot the bill, or will those costs quietly show up on your monthly utility statement? Thank you so much for joining me for this explainer. I really hope this THD framework helps clarify the very real physical challenges of our digital future. Keep a close eye on your local grid, and we'll see you next time.